Okay, well, I think we're about ready to start. Hello, everyone, and welcome to the April 2022 edition of the Underwater Acoustics webinar on behalf of the UCAN Plus Underwater Acoustics Special Interest Group. Today we have three presenters with us. We have Alfie Treloar, Hugh Rice, and Patrick Lyne. And they got three pretty diverse presentations coming up that I'm really looking forward to see. So today, just to let everyone know, we'll be having a bit of a different format where will have their presentation. And then for the last quarter of this hour, then we'll be taking questions. So feel free to either write those in the chat as we go or save them to the end. And then I'll forward them on to the presenters and we'll go from there. Okay, so first up we have Alfie. If he is ready to share his presentation, then we'll get started.
Hello there. This will stop on the screen sharing. Yes. Share sound, screen one. All right, can you see that? All good?
Okay, we can see it.
Cool. All right. Okay, yeah, so hi, I'm Alfie, and this will be just an overview of the work that was the core of my research soundings submission, which was titled Dynamic Complicated Propagation Modeling. And this work was carried out as part of my PhD at the University of Bath with the support of Autonaut and Seish. So I'll just start by giving some background on my PhD work to provide some context, and then I'll give a brief overview of the simulation process that I developed, light on maths, so don't panic, followed by a look at the experimental validation of it, and then finally the focus of the presentation will be a more in-depth look at my research soundings entry. So firstly, some background. So my PhD work was focused on the use of passive acoustic monitoring techniques from an Autonaut uncrewed surface vessel, which is what's shown here in this video. And it uses a clever mechanism to directly convert hull motion from waves into thrust, even in the directional waves as shown here. And with the solar powered sensor payload, it's capable of extremely long duration missions, up to many weeks at a time. And also, being wave propelled, it has an extremely low acoustic signature, which makes it uniquely capable for passive acoustic monitoring purposes. So for this purpose, Seish developed a number of acoustic arrays for use with the Autonaut, which are short and light enough, so one of them is pictured here. Short and light enough, they won't interfere too much with the propulsion. And these arrays can be used for applications such as detection and localization of marine mammals or divers or submarines, and that kind of thing for port and harbor security or marine mammal mitigation, those kind of applications. And this is the array being deployed in a trial I was involved in last year, which was a nice sunny one, unlike quite a lot of them that you go. It's usually a bit more wavy and rainy. So in order to investigate these challenges associated with operating passive sonar from a wave-propelled vessel, I developed a simulator intending to provide accurate data sets in order for me to develop and test algorithms. So the flow diagram for this simulation process was as shown here, and I'll just kind of briefly go over this at quite a high level. So first, I take my source signal, I generate a source signal. So in this instance, it's just a sinusoid, so a single tonal frequency. And then I compute the propagation time and the transmission loss using some kind of propagation model. So here I've shown an output from the Bellhop propagation model, which I'll discuss a little bit more later on in a later slide. And then also at this stage, I include the effects of the sea surface movement, so whether it's an oscillating sea surface or whether it's still. And then I use the computed delays to delay the signal via interpolation which efficiently captures the Doppler shift from moving arrays or sources. And then each of the generated signals for each of the targets, for each of the paths, can then be summed to generate a noiseless signal, received signal at the hydrophone. So this just illustrating summing some signals. Obviously, typically there'd be a lot more than that. And then the final step is to add some noise to each of the hydrophone's signals, which can either be white Gaussian or varying in frequency. So your final result is a simulated data for each hydrophone that, for example, could look something like this. So this simulation process was validated with some experimental data. And for this, we used the Unmanned Warrior trial, which was a large-scale demonstration of the capabilities of autonomous vessels off the coast of Scotland, which was run in 2016. And during this, an Autonaut was towing an 8 hydrophone digital array in the presence of an autonomous underwater vehicle, which had a projector which was emitting tonal signals at various frequencies. And the GPS track for the section where this was detected was as shown here. So essentially the AUV did a drive-by of the Autonaut. And the acoustic data from one of the hydrophones on that acoustic array is shown here. So the spectrogram, so this is a spectrogram with frequency on the y-axis and time on the x-axis. And you can see the presence of a number of horizontal lines which correspond to the source signal being transmitted by the autonomous underwater vehicle. So as previously said, this was used for validation of the simulation process. So the same spectrogram here. And then the GPS data, array compasses, and the noise profile was used to simulate a data set with a static reflective surface. So, so with a sea surface that's unmoving and reflective, which resulted in this spectrogram, and then again simulated with a wavy surface, so an oscillating sea surface. And notable from these is the interference patterns that on the still surface, which is less present on the wavy surface, with the reality being somewhere in the middle of the two, as you'd expect. And generating a higher resolution spectrogram shows the effects of Doppler from the moving sound source are captured, as well as some of the spectral bleed out from the tonal signal. So that you can see it modulates in frequency as it travels past the array. Again, with the true data being somewhere in between the two. And computing bearing estimates. So as I said before, if you've got an array of sensors, you can compute, you can localize your sound source, and computing bearing estimates for each of these data sets. So this is a slightly different plot. So you've got time on the y-axis now, and bearing on the x-axis. And you can see the detection of the sound source as it travels past the array. So it travels from -45 to 45. And then there's a multipath, which is caused by a surface reflection. And these are both clearly replicated in both the simulated data sets, again, with the reality being somewhere in between the two. So finally, on to my research soundings entry, in which I use this simulator to demonstrate some of the interesting phenomena that can happen when you when you simulate the propagation of sound underwater. So for my entry, I made a source signal, which was me playing the Tetris theme on one of my guitars. So then I took that signal and simulated its propagation from the source, which is denoted here by the Game Boy, to the hydrophone, which is shown by this microphone. And then I gradually moved them further apart out to a distance of 1 kilometer. And so now to demonstrate the kind of the difference in using different propagation models, we'll compare kind of 3 of them in terms of the output that they produce. So in this first instance, I'm using a spherical propagation model, which is a simplification that assumes the sound propagates uniformly in all directions, and so is typically used for close range modeling, as it only considers the direct path between the source and the receiver. And the result, as shown here, is a severe drop-off in the magnitude of the received signal as it reduces with the square of the distance. So even after a couple hundred meters, the source signal completely drops off. And then it's completely undetectable. And that's because the magnitude, so the transmission loss increases with the, basically the magnitude decreases with the square of the distance rather than because it's spreading out in a sphere. So another simple model for propagation is known as cylindrical spreading, which is basically beyond a certain range, the acoustic waves will hit the sea surface and the sea floor. And then the acoustic energy is contained within those boundaries and is assumed to spread out as the surface of the sphere. And this results in a vastly different magnitude receiver, still being very much detectable for the entire duration. And notable here as well is that this is just it's basically just a magnitude scaling of the output. There's no interference captured, and no other phenomena that are captured. And then finally, the propagation model that I used in my entry is known as the Bellhop ray tracing model, which simulates many different paths from source to receiver to produce potentially a more accurate simulated data. So in this instance, I put both the source and the receiver at 20-meter depths, and I put them in the water column that was 35 meters with a nonlinear sound speed profile, which is the reason for this curving propagation. So each of these, each of these lines is denoting a path from source to receiver. And the blue line is showing the curved propagation due to the sound speed profile changing from the surface to the seabed. And this is this is a relatively dramatic change in sound speed, but it's not out of the ordinary to have such a vast change in sound speed in summer months, when typically the sea surface is quite a lot warmer, and so the speed is a lot faster at the surface, and then it drops off with depth for a bit until the pressure takes over. So so it's a relatively dramatic change in sound speed to effectively to amplify the thing that I want to demonstrate. So the simulated data set for this sounded like this. And a few notable things occur in this data set, which were not captured at all in the previous simpler models. The main one being the dramatic kind of non-linearity of the receiving magnitude. So for example there, the magnitude increases to almost that of the beginning of the data set, and then drops off completely at around 700 meters, only to increase again in magnitude again at the end. So this kind of dramatic non-linearity with range occurs because of interference patterns of the multiple propagation paths between the source and the receiver, and also because of the way in which the sound's propagating through the water. So this demonstrates just kind of one aspect of the importance of accurate acoustic simulations for experimental trials in order to kind of ensure their success and not be hit with unexpected acoustic phenomena. And yeah, that's all from me. Thank you very much. And yeah, if you have any questions, I think we're doing them at the end.
That's right, yeah. Questions in this case we'll be doing at the end, so we can capture them for everyone at once. Thank you very much, Alfie. It's very interesting, very interesting. Okay, so next up we have Hugh Rice from the University of Leeds. Hugh, if you'd like to share your presentation.
Okay, can you hear me okay?
Yep, can hear you perfectly.
Thanks. See the slides okay? Okay, hello everyone. Thanks to Ben for the opportunity to speak. My name's Hugh. I'm a postdoc at Leeds. The research that I'm talking about today is from while I was in the School of Chemical and Process Engineering between about 2009 and 2019. Since then, I've been doing work on non-acoustics, if you can believe it. So this is about 10 years of work, covers quite a few topics, and it's kind of an overview. So from the Tetris theme tune to the common pipistrelle bat, this is a good illustration of some of the applications of acoustics, because they're bats are experts at acoustics. I've got a sound clip here from a pipistrelle hunting for insects, and it uses a lot of the same methods that we use as engineers, a lot of the same acoustic tools. So they can compute the time of flight through backscatter and speed of sound. They use the Doppler effect as well to find the relative speed of objects, so as in solid objects and their prey, so other winged beasts. And they also use frequency modulation, so they vary the frequency within the chirps, which allows them and us to look at the texture of things, so the colour, the sound colour of objects, if you like. So you should be able to hear this. I'll play this recording. This is a bat hunting for insects, and it's slowed down. So there you go. So you can hear at one point in the recording, there's a kind of a trill, which is what they call the terminal buzz. So that's when the bat's getting very close to its prey. So it increases its frequency and therefore decreases its wavelength. So it kind of hones in the closer it gets, so that it can grab the insect that it's after. So we use a lot of the same techniques in the lab. And so to the nuclear industry, the research that I did was kind of motivated by the issue of the UK's nuclear waste inventory, which is going to be very expensive to deal with. It consists of diverse materials, and part of the process of decommissioning and processing of the nuclear legacy waste consists of characterization. And flow assurance. So to be able to process it, we need to know what's there, and we need to know how it's flowing. And being very radioactive, some of it, and being very chemically dangerous and just mechanically dangerous to deal with, acoustic methods means that we can mitigate some of the risks to operators and the risk of unnecessary chemical or radioactive leaks. So that's what motivates the research. It's non-intrusive and potentially remote methods for flow characterization in weird and wonderful, potentially weird and wonderful flow geometries. So, and this is basically an overview of some of the papers that we've done in that decade. So the first is this, is a model for calculating the concentration of suspended particles, and in this case it was in a pipe flow. And you can see on the left there's a picture. In that case, when we say multiphase flows, we mean mixtures of solids and liquids. So that's water in the picture with some glass particles in, which are about 50 microns. And we use this model from Ocean Engineering by David Hertha from 2011. It means we have two acoustic transducers running at two different frequencies, and that allows us to back calculate the concentration of particles in a profile through the pipe. And the plot on the right is the concentration in kilograms per meter cubed, I think, through the profile, the inner profile of that pipe, and we got some good results. So it was interesting to be able to apply something from a different field to an engineering problem, even though it did require a bit of shoehorning. The second was in this case we used the backscatter again, but in this case we were interested in measuring the critical deposition velocity. So if you have a settled bed of particles in a pipe or another geometry, the critical deposition velocity tells you how quickly you need to pump the fluid for it to resuspend all the sediment, because the sediment might be radioactive, it might be chemically active, so it might be heat generating. So there are situations where you want to make sure it stays moving and it doesn't accumulate anywhere. And so what we did was, as you can see on the right, the critical deposition velocity depends on the concentration C on the x-axis, and at lower concentrations it increases. And so we were interested in finding a correlation between the flow properties, which are covered by the Reynolds number there, RE, and the material properties, which are covered by AR, the Archimedes number. So in practice, we measured the depth of the settled bed of particles in a pipe as a function of flow velocity. And the issue was that the literature on this was huge, but a lot of it was of very poor quality. So I developed this method that was very unambiguous, and it gave us really, really clear results. So whereas in some of the literature there's several 100% of scatter in the data, we managed to get everything to collapse onto a single curve on the right, using this one expression on the bottom right, and the phi on the right there is the particle, is the solid concentration. So it means that we've got really good confidence that we can predict what flow rate we need to pump stuff to make sure it stays suspended if we know all the material properties. And this is, again, a completely different topic. We used, in this case, Doppler Velocimetry. So look at the frequency shift of the emitted acoustic pulses. And the issue here is that usually to measure the rheological properties of a suspension, you'd have to take a sample. So you'd have to take it, take some, put it into a bench rheometer, and if it's hazardous, that's something that you'd want to avoid. This inline rheometry allows us to do it in situ, so we can just do it through the pipe wall. It makes it potentially safer for people to do, and it gives really good results. So on the left is an illustration of the difference between Newtonian and non-Newtonian flows. The dashed more sort of circular looking line is a Newtonian flow, and the data with the circles is a non-Newtonian flow, which is what we were interested in. And you can see that the flow profile is very different. So that's kind of the velocity profile. So you end up with the plug flow in the middle. So we used a combination of acoustic probes and pressure sensors, and that allowed us to calculate the viscosity, which is shown on the right, as a function of shear rate, which is related to the flow velocity, which varies across the pipe. And we applied this model, the HBE, which is a Herschel-Bulkley extended model, and we got very good agreement between inline and offline rheometry, which we did with a non-hazardous substance just for validation. Lastly, this is probably the most fun, because it was a combination of acoustic methods and visual video analysis methods. So I wrote some code to track the dynamics of this agitated tube reactor. So I'll just run that. Hopefully you can see that moving through Zoom. But this is an agitated tube reactor. So there's a black catalyst in there. It's used for intensification of chemical processes. So the black powder has it's actually carbon with a palladium catalyst on, and the inner tube, as you can see, is free, and the outer tube is driven pneumatically. The inner one is intended to agitate the particles to keep everything suspended, and the tracker points that you can see superimposed are for me to analyze the motion. And this is what it looks like, the lower one. Hopefully you can see that as well. This is when it's been through MATLAB. the inner tube, which is in red, as you can see, rotates and rolls as it moves, and it's partly that rotational motion and partly just the back and forth of the agitator that causes the suspension to remain suspended instead of just forming a bed on the bottom. And we used a combination of those visual methods and acoustic methods to characterize the dynamics. So at the top is a comparison of my colleague Yi, who did a computer simulation of exactly the same system, and which is the simulation, the red lines, which is compared with my video analysis data, which is the experimental data on the top. And we managed to get really good agreement, which is really a lot of fun. And the lower part is the acoustic part. So again, I used an acoustic probe, which you can see in the picture on the top left, which is attached to a clasp, to measure the RMS velocity, which is the root mean squared, which is a measure of the turbulence intensity across the horizontal cross section of the pipe. And the point there is that, again, on the left is my colleagues' numerical simulations of that system, and on the right are my acoustic experimental data of the same system, and the magnitudes are very similar. We've done a phase average there, so basically cut the data into 8 slices in each cycle, and then averaged for each cycle. And that was a lot of fun because we got such good agreement. So it's quite a diverse range of applications, but again, all motivated by the need for non-intrusive acoustic methods for potentially hazardous substances. So this last one isn't strictly nuclear, but still. And so that's a lot. I'm in Mech Eng these days, but there are some of my supervisors who are in SCAPE, which is chemical and process engineering. And if you'd like to get any more information, it's all there. So thanks very much.
Brilliant. Cheers, Hugh. Really interesting presentation. So that leaves us with, last but not least, Patrick Lyne. If you'd like to share your screen, and we'll see what you have for us.
Yeah, okay. Can you hear me all right on that? That's great.
Yeah, can hear you.
Yeah, perfect. Yeah. Email is there, patrick.lyne@iwdg.ie. If anybody's got any questions that you want email to me afterwards, I'm more than happy to take them if you can't, if you don't manage to get them in on this webinar. Also like to thank Tom and Jonathan Gordon for helping me with the hydrophone and supplying it to me on this one. So I basically started with the question, minke whales in Ireland. Is there any mating habits occurring in Ireland? What we know about minke whales is very little. They're the commonest baleen whale in the world, but relatively little is known about them. We think that they are calving roughly January and February for the Northern Hemisphere. So they have a gestation period of about 10 months. Therefore, they should be mating perhaps March, April, May. So I had a look at the minke whale sightings for the IWDG had recorded from 2016 to 2020, and I mapped them. And this is what it looks like. So you can see straight away there's a large cluster of sightings off the southwest coast. So I looked into those a bit in more detail, and I looked for aggregations of minke of 8 or more animals. Obviously, if you're going to get any sort of mating behavior, one animal's not going to do it on his own. So I'm looking for groups of animals. And when I looked at the aggregations, springtime tended to have more aggregations than any other time of the year. So spring being March to May, there's not very many aggregations occurring in March, and that's basically where I'm located down here in the Beara Peninsula, where you have one aggregation on the map there in March. But when we get into April and into May, the aggregations spread out, and typically off the Beara Peninsula in May, I don't tend to see as many Minke aggregations, and they seem to have spread further afield at that point. So I was looking for a hydrophone, obviously, that would capture the acoustics of baleen whales. So something that would work down to the low hertz levels. So I got Tom last year supplied me with Tom Gordon supplied me with a hydrophone that it's a HTI hydrophone that works from 2 hertz to 30 kilohertz, and unfortunately won't pick up this guy, which is a harbor porpoise, which, you know, they produce clicks from 120 to 130 kilohertz, so it's out of their range. And the hydrophone is connected to a voice recorder in a waterproof box here on the buoy, and that's recording up to 48 kilohertz. So yeah, it's a cheap and cheerful solution. It's not a huge expense. Most of the money on the system is in the hydrophone. So yeah, so what we were looking for was recording Minke whales, particularly the Thump Trains, which are going from 50 hertz to 250 hertz. And this Minke whale was, this was a photograph of one going past the recorder last weekend. Unfortunately, he didn't produce any Thump Trains at the time, so they're not always acoustically active, which is a bit unfortunate because it's been quite difficult to record Minke whales, it seems, in the Eastern Atlantic up to this point, although on the US side, they seem to be getting quite a few recordings of Minkes. So now this is a recording which I got last year. It's just a drop-down hydrophone on 10 meters of cable thrown over the side of the boat, fortunately in very calm weather, so we don't have a lot of wave noise. And I just play it for you so you can hear it. I think. So you can hear the Thump Trains. That's these guys here at the bottom with red markers. The 50 to 250 hertz scale is here, frequency scale is on the left. You can hear the high-pitched whistles and double peaks, they're always around. So yeah, there's always this background noise from them. And then you get these clicks that are coming in. These are also Minke. So these had a peak frequency of about 10 kilohertz. A little bit unusual because I've not seen clicks like this described for Minke whales anywhere. There was clicks have been described with a peak frequency of 5 or 6 kilohertz, but not 10. So it's a little bit different, but it's just probably the Irish accent on the Minke whale. But yeah, so that was interesting, and that was recorded after about, I suppose, the hydrophone was in the water for about 1 minute and 43 seconds, or 1 minute and 44, something like that. So it didn't take very long to get a Thump Train, which have proved pretty elusive on this side of the Atlantic. So this year I tried to be a little bit more, well, take it to the next level. So I got another hydrophone of the same type on 20 meters of cable to get it deeper, to get away from the wave noise. So so far this year I've only managed to deploy it once. It's been out drifting for 3 hours, so quite a short time. But again, we've got several Minke Thump Trains. I'll just play one. And that's considerably fainter, and as Father Ted would say, that's because it's far, far away, Dougal. But yes, so so yeah, in 3 hours we managed to get a number of Thump Trains. I have I'm not exactly sure how many, to be honest, at the moment, but we've got 3 or 4 Thump Trains in a 3-hour recording. And there's a number of other acoustics as well, which I would describe as whoops, cries, and some grunts, which initially I thought were from a humpback, but we don't have any humpbacks in this particular area at the moment. There are some further along east along the coast. They're not within 50, 60 miles of here. So I'm sure I'm not seeing any humpbacks around here. Humpback, but it's flowing as well.
Oh, Patrick, I think we might have, I think we're losing your signal a bit. Can you hear me? Alfie, Hugh, are you able to hear Patrick or? Okay. Just give it a minute, see if he manages to reconnect.
No, he's frozen for me as well.
Just.
Are you there, Patrick?
Yeah.
Okay.
Patrick, are you there?
I can hear you, but I don't know if you can hear me.
Oh, I think we might have you back. I could hear you then.
Yeah, I'm not sure.
The audio is still a bit messy coming through, I'm afraid.
Yeah. That's...
Perhaps if you try to leave the Zoom call and then join back in, it might be a bit better.
I don't know. You hear me now? It's a bit weird.
Still a bit robotic, I'm afraid. I think perhaps for now, if we take some questions, if anyone's got any questions so far for Alfie or Hugh, now might be a good time. If we have time, we can come back to Patrick at the end. So, if anyone's Patrick, if you try and reconnect, then perhaps the connection might improve. But for now, if anyone has any questions for Hugh or Alfie, if you scroll to the bottom of the screen on your Zoom client, there should be a chat box that comes up. And if you leave anything in there, then we should be able to see it. And I can pass any questions on. But I can kind of get us started. Alfie, I had a quick one for you. So you mentioned 3 different models that you use. I think it was spherical spreading, cylindrical, and the last one was Bellhop.
Yeah.
It seemed like the Bellhop one was the most kind of sophisticated, as I could tell. Are those cylindrical and spherical ones actually used in the industry at all? Or?
Yeah, they're useful for very quick kind of back of the envelope calculations for working out like transmission losses for fairly simple cases. But for example, so what I didn't actually demonstrate in my presentation or in this simulation is that the Bellhop model can also take into account terrain in the seafloor. and how the sound will propagate around that, because obviously you end up with some unusual reflection patterns and interference patterns under the water, which obviously aren't captured at all by simple like models such as cylindrical or spherical spreading, but they are still very useful because they're quite basic, and generally it will, like as a rule of thumb, it will be kind of somewhere in between the two of them for most propagation scenarios. But yeah, there won't be won't capture all of the acoustic phenomena that happen. So yeah, I'd still use them because they're also significantly quicker to compute. So yeah, like kind of orders of magnitude quicker in terms of my simulator to compute using those simple models.
Yeah. Okay. And for the Bellhop model, is it kind of appropriate for use in any sea and ocean, or is it kind of like more specifically for use in the North Sea or the Atlantic Ocean, something along those lines?
It's appropriate for kind of anywhere. You can customize your scenario entirely from your seabed composition to your sound speed profile. So it's like scenario agnostic, but yeah, the main things that change obviously are your sound speed profile and your seabed composition, which changes how much reflection you get of the acoustic energy. So yeah, you can modify it to simulate anything or to model anything anywhere.
We've got a question that's come through from Ben Thomas for Hugh. Hugh, are Sellafield planning to implement any of your methods in the coming years?
Well, I've not worked on acoustics the last 3 years, so I can't say for sure. So I've not been in touch with anyone from Sellafield for quite a while. But one piece of research that we did do that I didn't cover in the presentation was so yeah, short answer, they're trying to, I think. A bit of research that we did was to apply some of these acoustic techniques to a mock-up of a settler tank that they do use at Sellafield. So it's a big cuboid tank of water and sediment. I think they used clay when they were on site, and they mixed it all up and then let it settle in this tank. And then we used an array of acoustic probes to track the dynamics of the settling front and to sort of to characterize how it settles and spatially as well as over time. And so yes, that was a kind of a pilot test of some of the technology. On the other hand, I think some of the technology that they do use on site may be proprietary, and they have a lot of their own in-house people that do this. But so yeah, short answer, not that I know of for sure, but the potential is huge because there's tens of billions of pounds involved potentially, and yeah, it's a long-term program at Sellafield, and the reason that acoustics are so useful is that they're actually relatively cheap compared to some like optical and laser-based methods. They're non-hazardous. They're so cheap that the probes and things are almost disposable if they do get damaged by radiation or whatever. And they don't require a lot of computational power either. So I did a lot of the analysis just on a laptop, and that's generally the case, so that you can. So yeah, there have been one or two other bits of technology that developed at Leeds that they've used, and in fact, some of my colleagues in electronic engineering, I should say, have developed a bespoke ultrasonic signal processor called the UARP. So that's if anyone's interested. That's been developed by Stephen Freer and David Cowell in electronic engineering. It's really state-of-the-art stuff, multi-channel, multi-frequency acoustic signal processor. So yeah.
Fantastic, thank you. And I see we have Patrick Lyne back on the line, and your video is looking clear and crisp. So can we get a quick audio check, Patrick?
Yeah, I just corrected my name again. Seems I will put that back. Do you want me to finish off? There wasn't much left, or shall I?
No, I'd love for you to finish off. Absolutely.
So I'll just go back to share screen. I don't really need sound, so yeah, it was just I just wanted to make the point with this was a screenshot of the spectrogram for that last pulse train, that Minke Whale pulse train, which is down there at about, it's about roughly around, that's centered around, say, 220 hertz, roughly off the top of my head. And this is just some boat noise. Actually, I think it's our own boat, but because where I'm located, it's near to Castletown Bear, which is one of the main fishing ports in Ireland. There's a lot of vessel traffic going in and out of the port. It's not a hugely busy port, but every time a vessel goes by, it could obliterate 20 minutes or more of the recording, because you've got too much sound down here in the low frequency from the boat or from the vessels, from the trawlers. And it is just noise. It just highlights noise as an issue for these animals. If these animals are using these thump trains, as we think, for mating calls, then the female's not going to obviously hear the male. And as noise increases, it therefore becomes an issue. And what we have in coming up in Ireland over the next few years is a huge amount of wind farm development. And that will involve typically a lot of piling noise or pin driving noise, perhaps for floating wind farms. And, you know, there's a requirement in Ireland to do a minimum, well, there's a requirement to do 3 years of acoustic data, baseline data, before you develop a wind farm. However, there's an to record acoustic data for environmental baseline surveys. And FPODs, which the precursors of which were CPODs, the precursors of which were TPODs, are very good at recording clicks. But thump trains and whistles and acoustics such as that baleen whales in particular produce are not really picked up by FPODs. So there's a need for sound traps or some other form of acoustic recording for baseline data, with you know, for the development of offshore renewables. So it is something that we, I guess, in the Irish Whale and Dolphin Group would like to see done for baleen whales, as well as for the likes of harbour porpoise and dolphins, which click more frequently. Drifting buoys are, I think, also a possible solution for recording baseline data. Not in some ways as good as static, which give you 365 days of the year recording, but drifting or moving recorders allow you to cover a larger spatial area. So, and typically with drifting buoys, or if you've got like Alfie's got the Autonaut with that, you've got less data typically to analyze. So that can reduce the workload somewhat. But you know, whether that's acceptable to regulators is something that remains to be seen. Particularly here in Ireland, we're still guessing as to what they'll actually require. But yeah, that's it in a nutshell, really.
Okay, fantastic. Thank you very much, Patrick. I'm happy we managed to get you back to finish off. So now we'll be going back again to the questions segment of the webinar. Again, if anyone has any questions, please just take your cursor down to the bottom of the screen to the chat section, and feel free to write anything in there and I'll convey it. But in the meantime, a question came through for Patrick. From Artash. Hi Patrick, can you determine from the spectrogram whether the acoustics was created by a single Minke/humpback whale or a group of them? And if there are multiple whales, why is the acoustic pattern so uniform? Are they vocalizing in chorus? Thanks.
I mean, if I have two thump trains, if I have two thump I'm not going to be able to say two thump trains. If I got three thump trains, I'll try 4. If you've got one, or if you've got more than one thump train, you're not really, I mean, not with a single hydrophone, you can't get directionality. So you don't know whether it's coming from a different direction or not. So you don't know if it's one or more animals, unless you've got 2 thump trains overlapping, in which case you obviously know it's coming from different animals. I mean, the thump trains I believe are coming, well, from last year certainly were from Minkes, because there was no humpbacks around at the time, and the thump trains were loud enough that they had to be, the animal had to be quite close. There's other acoustics there this year, and even last year, that are more reminiscent of what's been described for humpbacks, but I'm not sure that we really know the full range of acoustics that Minkes produce. So I'm not completely convinced that some of the hoops that I picked up at the weekend, that they're not coming from Minkes, to be honest. They could be. When you look at the research into humpbacks, it matches quite well into what the sounds that humpbacks produce, and there's relatively little research done on Minke acoustics, so the same amount of data isn't there to do that sort of comparison. And I think the thump trains are coming from Minkes, to be honest. I'm not finding at this time of year when we're getting the thump trains, we're not seeing, we have seen humpbacks in the past, so they could be, 20, 30 kilometers or more offshore, and we might be detecting them. I mean, the hydrophone's fairly sensitive, but yeah, so I don't know.
You mentioned at the start of your presentation that you kind of gone together all the sightings of the Minke whales around the coast. Is there kind of like an official framework for that, or is that, like, how do you organize all of that information?
Yeah, I should have said, actually, I think those sightings along the coast are quite biased. They're coming in through the Irish, they're recorded through the Irish Whale and Dolphin Group sightings program. But what you tend to get is, you'll have seen there's a cluster around the Bear Peninsula, that's me, and you'll have seen a cluster around the Dingle Peninsula, that's Nick Massett, and you'll have seen a cluster down around the south coast, and that's largely Colin Barnes and perhaps a few others who are running whale watch operations, and they're probably slightly biased to starting around Easter time, so there might be sightings in March, early March, that are maybe missed because Easter's in April this year. So there's a certain amount of bias in the data, I suppose. But yeah, it's coming through the Irish Whale and Dolphin Group sightings program. There's an app to report sightings, and there's also, you can report through the website.
Oh, fantastic. So Stephen Comfort has a question. He says, Patrick, would there be value in using multiple drifters to achieve directionality? Could be useful to ascribe sounds to particular animals / species. Yeah,
I mean, I think multiple drifters are the way to go, absolutely, for sure. And there's other ways of using drifting buoys that I would really love to play with, to be honest. I think drifters could be hugely useful for beaked whales, for instance. And Jay Barlow in the States has done that, and done it to use to get density estimates for beaked whales. And they're a very cryptic species, very difficult to get information on. So they could be very useful for that. And I think multiple drifters would be the way to go, because you could get directionality, and you would get some sort of idea of density of animals as well. And you get a lot more information from 5 or 6 drifters than you would from one. Unfortunately, I can't afford 5 or 6.
Hugh, I had another question for you, actually. Regarding all these the different methods that you mentioned, because I think we're mostly talking in regards to was it Sellafield? Sellafield or Sellafield? I think it's field.
Sellafield, yeah.
Sellafield. Do you know if any of them since have been used at other nuclear power plants?
Not that I know of, no. And the only reason I really mentioned Sellafield is because the vast majority of the nuclear waste in the UK is stored there. So they've got kind of the greatest motivation to use these methods, but no, not that I know of.
Is all the nuclear waste, is that all from there, or is it kind of? stored?
No, it's aggregated there. There is some elsewhere in one or two places, but the vast majority of it has been aggregated at Sellafield. And a lot of it was produced there as well, because that was sort of the site of Windscale originally. But yeah, the vast majority of the waste, and that's where it's been stored up till now, most of it. So there's one or two other places like Copenhurst in the northwest, but yeah,
okay.
So most of it is.
Yeah, so that scale of waste to kind of get through isn't necessarily typical for every pattern.
No.
Okay.
There's one or two sites which have been effectively completely decommissioned or returned to, if not returned to brownfield, but close to being returned to brownfield, apart from the reactor core itself, which is not the case at a lot of the Sellafields there.
We've got another question that's come in. It looks like it's a bit of a combination one for Alfie and Patrick. Would Alfie's computer simulations with Minke Acoustics produce interesting / helpful results?
Well, the short answer is yes.
Yeah, so I think, well, it depends. So for my own research, I've typically used my simulator to test processing algorithms for for localization and this kind of stuff, for like the run up to trials, to or to validate against trials, or to have a performance, an estimate for the performance of the system prior to doing the trial. So yeah, in that sense, if there were, obviously if there were the possibility of implementing some form of system, you could do a performance assessment in simulation prior to implementing it, would probably be what I'd say in terms of the most use for this simulator for Minke Acoustics. Because the stuff obviously that I showed is single hydrophone simulations, but for me, most of my research is in multiple hydrophone arrays and localization using those. So that's how I predominantly use my simulator.
I mean, you can't do localization on from a single hydrophone. So your multiple hydrophone array would be, from my point of view, would be extremely useful at this point of time, because I could say where these unusual acoustics are coming from, and we could go out there and have a look, sort of thing, but and see what animal is actually producing it. At least go in the right direction.
Yeah.
Yeah, Alfie, some follow-up question as well. Because I've a few years ago now dipped my toe into the world of simulations and everything. So I'm familiar with the name Bellhop. I know there's a few others as well. I remember RAM, Geo, and Kraken, and others like this. Was there a particular reason that you went for Bellhop?
So I went for Bellhop predominantly because it would capture the so the frequencies I was working at, it was one of the most applicable ones, and also the way that I've implemented it captures the effects of Doppler shift in the final data set. The other ones typically result in a transmission loss, but you get the time of arrival with ray tracing. So it was predominantly because it computes the time of arrival for each of the propagation paths, which is what I was interested in for capturing a proper accurate data set for a moving source. So because of the extra information, basically.
Okay, great. Actually, I have a last one for Patrick Lyne as well. I'm kind of jumping around a bit, I know, but I was wondering, with the Thump Trains, is that the only noise that the Minke whales produce, or is there a particular purpose for the Thump Train in particular that we know of?
Well, it's believed that it's just the males that produce the Thump Train. So it's like with baleen whale acoustics, it's usually the males that like the humpbacks do all the singing, but female humpbacks do produce some sounds, but they don't sing. And they think effectively that the Thump Train, well, the thinking is that the Thump Train is similar to the humpback singing. It's the mating call. There's a number of fish that produce like similar sounds to the Thump Trains. So it's just the it's basically a mating call. There are other sounds, but these are not terribly well described in the literature that I've found so far. The one that everybody tends to concentrate on for Minkes is thump trains, and you know it is. I mean, they can mate at any time of the year, and they could calve at any time of the year, but they have preference typically for calving in the winter months, and we think in warmer waters. Yeah, the picture is only just emerging, but you know, I don't think we don't know very much about Minkes at all. There's a huge amount to do in comparison to some of the other less common species that we know a lot more about.
Yeah, and I think, because I know we're at 3 o'clock now, but there's one last question that's come up in the chat from Craig Stenton. Hi Alfie, can the model be used in reverse to try and determine source level based upon distance estimates?
Yes, I guess you could go either way really. I guess you could use the estimated source level to determine the distance, or vice versa, depending on what you want to estimate. But obviously, yeah, if you have a distance estimate, you could distance estimate to your whale, I guess from visual sighting. I'm not sure how you'd have a distance estimate, but yeah, you could definitely get a decent estimate of the source level, I reckon. But yeah, depends. Yeah, I don't know what's mounted on that buoy. If you got a camera for range.
No, the buoy is pretty basic. It's got a recorder, it's got a GPS, and yeah, a couple of batteries to run the hydrophone, and that's it. It's very it hasn't even got a light. And it's going out tonight, so I hope nobody runs it over.
I'm sure it'll be fine. Yeah.
Okay, well, fantastic. That'll do it for the webinar today. I want to dearly thank our 3 presenters, Alfie, Hugh, and Patrick. I think they had a really great, kind of diverse lot of presentations right there, and I certainly found it incredibly interesting. If anyone has any further questions, I'll be happy to forward them on if you email me at the email that's on the screen for you now. And yeah, we should have another monthly webinar next month, and information about that will be on our website. Additionally, we've been recording this, so the recording should be going up on YouTube at some point, and the link to that will be on our website too. So you can feel free to share that around. You can play that at the next family gathering that you have for everyone, if you'd like as well. So yeah, another thanks for everyone for coming out and watching, and thank you very much.